obviously, I'm Liam, and I've done my dissertation on the use of remote sensing and the estimation of turbidity in waterways. So in terms of this presentation itself, it's going to be like a little bit of introduction about like what is turbidity and why it's important. And then we're going to talk about the satellite monitoring of turbidity, and then my project followed by some of like the strengths and limitations. So first of all, turbidity. So what is turbidity? So turbidity is a qualitative measure of the amount of suspended sediment in a waterway. So this suspended sediment causes light attenuation or reflection, like backscattering of light. And this reflection has a bunch of effects on the environment, such as like it reduces the vision capabilities of like sighted aquatic organisms, and it also reduces the light availability for photosynthesis. As well as this, the sediment itself can also cause like benthic smoldering and irritation of fish gills, and just general increased depositation levels prompts the riverbed, which changes your environment. So why is turbidity important? So within the NES, we're not allowed to have a conspicuous change in colour from forestry operations, and a more like qualitative measure that's sometimes used is about a 40% allowable increase in turbidity. But we're not really too worried about the actual rules within the report. It's just to show that we care about it enough to regulate it. So in terms of current monitoring, NIWA monitors about 95 to 95 different waterways across New Zealand, and this said that it is on a monthly basis. So they're developing this really low spatial resolution and low temporal resolution compared to what we could do with satellite turbidity. So why would we be interested in doing it with satellites? Well, we've been able to do it since 1974 with these ocean color satellites, and we've gotten pretty good at it. So we are getting an average errors about 6% between your in situ and your estimated turbidities across like really, really big areas, which is awesome. And we are developing these really high spatial and high temporal resolution data sets, because every time we get an image, we can also get a turbidity estimation. There's no in situ testing required, and we can also get to remote waterways or really hard to access places without having to actually go there ourselves. And there's also the possibility to track along the length of a waterway. So say, for example, if you track down the length of a river, you could see the points where the turbidity changes, and perhaps that way you might have a point source of pollution. So this here brings me on to a very holistic view of why you might like it. Imagine this: PlanetScope's goal is to take global imagery of the world every single day. So with New Zealand's weather, we might get a good image, say 1 in 3 days. From that image, we could zoom in and say this little red square on our bottom right-hand side here. We zoom that there up, we've just got a traditional river, and we could get turbidity readings all the way down that river every single day. And we could also get the little tributary on the right-hand side, as long as our spatial resolution is small enough. And we could also get the lake in the middle there. And it's this here: we can develop these really high spatial and high temporal resolution data sets all without going there, and at a really low cost. So within my project, the aim of it was to see if we can use remote sensing to estimate the turbidity of waterways in New Zealand. So first of all, there are a couple of steps to my methods. The first step was to contact 2 regional councils. I contacted Waikato Regional Council and Environment Canterbury, and got all the continuous monitoring data that they had. So I got 2 sites within the Waikato River and 2 sites within the Heath Coast Stream, and got the continuous data sets. So this is just turbidity readings about every 15 minutes over the period of the last 4 or 5 years. And then I went to PlanetScope and downloaded corresponding imagery, like satellite imagery, for these places. And then this brings me on to really the keystone of this paper that made it all possible, and this is Nijhatz's equation. And this is really important because it's the only generic multisensory equation for estimating turbidity. So what this means is the only equation that we have right now where you can go to a site and estimate turbidity without having any in situ requirements first. So other equations are more like indexes, where you correlate your band reflection versus like the actual in situ sediment, or like the chlorophyll A levels, for example. But this one here, you can just apply it to a location and it will just work without any of that in situ validation of your data as such. So this is an example of one of my sites. You can see the Google Maps on the left and the PlanetScope imagery on the right. And so you can see with this lower spatial resolution of like PlanetScope imagery, why it might be harder to sample your smaller, narrow waterways, just because it's so much harder to distinguish features in general. And then from here, I've done a band comparison. So PlanetScope imagery has got 4 bands, 3 of which can be used to estimate turbidity. So I estimated turbidity using all 4 bands and compared it to the in situ turbidity to see which one was the most accurate at giving my estimations. And it turns out the green band was the best, so I've used this throughout my project. And then from here, you've got to my actual like example of this results from a site. So on this image on the right, you can see the in-situ turbidity in blue and the estimated turbidity in orange. And then we've got a linear relationship between the two. So as you can tell, we're not getting the best relationship. We're only getting an R-squared value of about 0.26. But what's important here is that when our in-situ turbidity is increasing, we're able to, as long as we've got an image for it, like a data for it, we're able to pick up the that increase, even if we're getting the magnitude and the absolute value of that increase wrong. So this naturally leads me on to some of the limitations of it. So the first limitation is that spatial resolution. So sample a waterway, a single pixel must fit completely within the waterway. So for PlanetScope imagery, this is about 5 meters. But for as soon as you consider like how the pixel aligns with the waterway and stuff like tree cover or vegetation cover, this also affects it. So you're looking at like a more realistic, say for about a 5 meter spatial resolution, say about 10 meters, but we'd need some more research to determine this. And secondly, it's just an inherent limitation of spatial imagery as a whole, and that high turbidity generally occurs in bad weather or when clouds are present. And with satellite imagery, you're not going to get a photo when the clouds are present because you can't see the ground. So you're never going to pick up those really high peak flows of turbidity just because we can't get the data. And then finally, this last one is both a limitation and an opportunity because it's Nietzsche's equation. So this is it's currently calibrated for coastal moderately turbid waters, which generally have turbidities of about 80 FNU, whereas our waters we're generally looking at about 5 to 10 generally. And with this here, we can these environments are completely different because the sediment particles that make up coastal waters versus our inland waterways just reflect light completely different. It's different chlorophyll concentrations. So you're never going to get a really good estimation of turbidity using this equation in its current state. But that's just because it's currently calibrated for those coastal waters. And there's nothing stopping us recalibrating it for our inland waterways. And they've already done it for a range of other waterways, a range of other coastal environments across the world. So in conclusion, it is possible, my paper has shown that it is possible to estimate turbidity in waterways from satellite imagery. However, we are limited by the spatial resolution of our imagery and our knowledge of waterway sedimentary particles. However, my dissertation has shown that we can do it, which is really cool because it hasn't been shown in any other literature yet. Pretty neat. And then with some further research, we can develop the technology further to create these really high spatial and high temporal resolution databases, which can have really far-reaching applications in environmental monitoring. Cheers.
Nice presentation. Gilroy, yeah, very nice. Questions, Mr. Harvey? And sorry, I should also recognize that while I guess I take the class, Campbell Harvey here also helps out in mentoring a number of the projects as they have progressed through the year. So question from you.
Okay, what is there any opportunity for webcam-based imagery? Would that be useful for us to take out this issue with cloud cover during the rainy days?
So just so the question was, could we actually use a webcam as opposed to the satellite to remove that cloud cover type issues?
In terms of past with other sensors, like issues with other past sensors, like originally when CubeSat first launched, like your NIR band had about 40% radiometric inconsistencies, and your read band generally has about a 10% radiometric inconsistencies, and that's what you're generally using for estimating turbidity. So I guess it would depend on how like radiometric consistent your webcam was. Yeah, so as long as you could have a really consistent, yeah, it was consistent in picking up the same colors, you theoretically could estimate turbidity from, because it is just an image.
Good. There you go. Very nice technical answer. Excellent. Other questions? Also from our colleagues. Anybody on Zoom have a question? Again, do feel free to jump in. Okay, Mr. Wood here.
Do you think that like satellite technology improves the resolution will be smaller, so you can see this image?
For sure, like even with PlanetScope, like they launched 2016 at 6.5 meters, and that's free for us to use. That's pretty unheard of maybe like 10, 12 years ago. So it's just increasing at a rate that we can't predict how small it's going to go. We can get down to like 1.5 meter resolutions at the moment. It's just that it's in these small constellations, which are quite expensive at the moment. So I chose this data because it has a lower, like a relatively low cost that would make, if you didn't have the low cost in the first place, sort of defeats the purpose of the project.
Is your data set built from aerial from satellite imagery that has zero clouds whatsoever, or is it a partial cloud cover? Do you get some sort of reflectance of surfaces?
Yeah.
So sorry, the question to Liam was whether or not his data set was always without cloud cover, or if there was a mixture of clear and cloud cover.
So it was initially chosen to be less than 60% cloud cover of the overall scene planet scope. So that scene might be like 100 k's, 100 square kilometers, for example. But then it's also just a visual inspection of the site to see if there's cloud cover there. But you can actually get automated AI tools if you were to automate the process, which you'd have to if you're going to develop these large scale things. Automated process which to detect cloud cover, and then it's more just like a true thing of, is that a realistic value that's match up with what we've estimated previously.
Last question, yeah.
Do you think councils are moving down this pathway to, in terms of freshwater legislation or regulations, to try and be able to measure more quantitatively?
So sorry, the question was, yeah, whether or not regional councils are moving or considering adopting this type of technology for their regulation. That's a good question to ask Liam, since he worked with Environment Waikato not too long ago.
In terms of other areas, I know they're using satellites to monitor land use change and stuff like that. So they're definitely interested in land, like satellite monitoring in general. And I would say that in terms of, if you look at the environmental value of being able to get this data set, they would be interested. But at the moment, it perhaps might be out of their reach because we don't have the calibration of those equations yet and the data set showing that it works. But I believe they would be interested if you had the research to back up your, like the validity of your data as such.
Thank you.
Doesn't the land use monitoring cover the risk of turbidity as much as monitoring turbidity does?
I'm not sure I understand that. Sorry.
Well, we know where you're going to get turbidity. We know what happened on the land. It's going to generate turbidity.
Yeah. Yeah.
So doesn't land use change, monitoring land use change actually predict the risk of increased turbidity?
So the question from Trevor Best is whether or not we should be focusing also on land use change, because we know that land use change increases that risk of water turbidity. Well,
it would be, but then you could also, this is more applications in that you could also get like those really like safe in the Alps or something like that there. So a more general overset overall. So that will definitely be a big driver of turbidity increases. But say, what if just a farmer decided to put in, he's been farming for 30 years and all of a sudden he started discharging his silt pond into the nearby river, and we could detect that. That should be cool.
Okay, with that, thank you very much, Liam. Excellent presentation, and yeah, congratulations.